So this talk was prepared by me and Juan Felipe Rodriguez Vasquez, who is also a machine learning engineer as me at Factor. So we decided to name this talk Find Love Watching Movies, which is about how embeddings can be applied in recommender systems and improve candidate retrieval in a dating app. We already have my presentation, but a little bit about me. I work in the data world since 2019. I'm working at Factor, and like more personal stuff, I'm passionate about leadership, books, dancing, art, and also beautiful landscapes. I'm 26 years old. I'm a paisa that really loves Bogota, so that's why I live between Medellin and Bogota. So let's say you're an intern at movies.com and you're asked to build the recommender system for this app. However, that's not all. So they just released a marketing study where they found that users are really interested on dating apps. So from movies.com, they ask you, why don't you also develop a kind of dating app for an app? So we will not be only able to recommend movies, but we will also able to recommend users to other users. So in order to develop this solution, we should have a review of recommender systems. So we decide how to tackle this problem. So these are like the basics of recommender systems. So we usually have user, items, events. So for users, we usually have the user ID in order to identify all the unique users. We also have some metadata related to the users, so some demographics like age, country, also a little bit about the interaction of the user, like last activity date. Then we also have items. Here, we also should have some IDs for these items in order to identify unique items. So on the context of movies.com, our items will be movies, but if it was Spotify, then our items will be songs. So here we also have some metadata related to our items. So for movies, we will have tags that describe this movie, categories, and also the release date of the movie. Then on recommender systems, it's also super important to have events, which gather like these interactions between user and items. So these events could be explicit or implicit. So explicit are the ones that we usually know, which are likes, comments, ratings, but implicit are the ones that are a little bit more difficult to catch because they are more related to the views of the user, when they do a click, for example, on a retail page or on a YouTube video when a user, because I think we all are that user from YouTube that always watches the same content from a YouTuber, but we never follow, we never do like. So how does YouTube get to know what are your tastes? We're taking this implicit feedback. And then we also have the intent. So what are we doing on the on our interaction? The intent of our interaction, which will be the searching a movie. So this is like a common pipeline on recommender systems. It's not the only one, but here we could see like two of our main tasks. So in a recommendation problem, we usually have like a big space of items, and then we have the candidate generation or candidate retrieval, where we take these millions of items and reduce them to hundreds of items. Then we have the second task, which will be the ranking, where we take this subset of items and we sort them according to a metric. And then we get like a final list of the items that we want to recommend. So for the candidate retrieval or candidate generation, we have these metrics. So I like to compare this candidate retrieval to a classification problem. That's why we have these metrics that many of us are very familiarized with. Factorized of K, precision, recall, accuracy. So for example, if you know factorized of K, it's like how many times a relevant item appear on K recommendations. So it will be like a precision that stops at K. Then for ranking, as you can kind of see from the word, it's really related to sorting. So these operations, as you may know, are very computationally expensive. So that's why the candidate retrieval is a super important stage, because otherwise the ranking will be super expensive. Imagine having to order or sort millions of items. So that's why candidate retrieval helps us to get a smaller set of items, and then we use metrics like mean reciprocal rank, discounted cumulative gain, and all of this in order to evaluate the sort. So for example, mean reciprocal rank, it measures like the first occurrence of a relevant item. So for example, if in a recommendation of 5 items, the first relevant appears on the 3rd position, the mean reciprocal rank will be 1/3. Then the discounted cumulative gain, it also looks at the position, but also it looks at the score. Normalized discounted cumulative gain, it kind of searches for the ideal ranking of our items. And then it measures from the list that we rank, how is the distance to the ideal list of ranking. And then P found is the probability of finding a relevant item. So we have these metrics in order to get the items that maximize this metric, and in our case that will satisfy the interest of our user. So a little bit more of review. So the classical recommender systems that we usually know are, for example, the content-based filtering. So this one uses item features to provide recommendations. So it's based on the principle of if a user likes a certain type of content, then he will also enjoy this kind of content in the future. So here we select kind of manually, we identify what are the features that describe our items. So for example, it will be genre. So if a user usually likes horror movies, then these models will try to also recommend horror movies. However, as you may see, these recommendations are very limited, so they are not very accurate. Because here we are not taking into account the interactions that users have with the items. So usually these models tend to recommend the most popular items, so they are not very accurate. So you can go next. Then we have collaborative filtering, that is a little bit better. Here we are considering interactions between users and items. So here the principle is that if 2 users have ranked positively or very similar a certain type of items, then they will also enjoy the same type of content on the future. So similar users are recommended the similar content. Collaborative filtering tries to find the patterns between users and items based on their interactions. So that's why here we have, this is an example of one of the models that we usually use in collaborative filtering, which is matrix factorization. So we have users and we have items. Green dots are the interactions. So as you can see, here we have also a problem that we have a lot of sparsity because, of course, users don't interact with all the content. So, for example, on Spotify, you may listen to a lot of music, but not to all the music on Spotify. So most of the content doesn't have a rating on our interaction feedback. So here the goal of matrix factorization is to find, to decompose this matrix in 2 other matrices, using some machine learning models, for example, in order to identify these latent factors, because here we don't know which are the explicit or specific features that correlate users or items. So that's why we call it latent factors that we discover using an approximation function like cosine similarity, for example. So we have a lot of approaches on our traditional recommender system. So we don't only have content and collaborative filtering, we also have knowledge-based models that are more based on hard rules or also heuristic approaches. We also have model-based, which are explicitly defining models, for example, machine learning models or statistical models, Bayesian models. So there are, in the literature, you will find like all sorts of combination of these approaches in order to improve the recommendation and capture better like how to describe an item, a user and their interactions. So these are some of the limitations that I have already mentioned a little bit. We also, the limitations of traditional recommender systems. So we always have the cold start problem that happens when we have a new user on the app, for example, because if it's a new user, how do you know like what to recommend to that user? Because he hasn't have any interaction. So we usually recommend the most popular items. Then we also have the cold start when we have a new product. Like, so how do you recommend that product if nobody else has rated? So there you could use the features of the product. Okay, so we have also a sparsity problem, as I mentioned, because we don't always have like interactions between, all the interactions possible between users and items. Then we have also lack of personalization, where when we are limiting our models to only focus on features from users or items, but not interactions. Sometimes we over-reliant on explicit feedback, so we are not taking into account like implicit interactions. And sometimes we also don't consider contextual information from our users of our movies that could be very useful. So that's why it's very interesting, the proposal that we have from the recommender systems. So here's what I call in the world of embeddings. So as you may know, the ones who have experience with deep learning and neural networks usually try to build embeddings in order to perform a task. So we usually have some features here on the left. Then we transfer them into embeddings through the second layer until the last one. And then we take those embeddings and use them to perform a task, which could be classification or regression. Then, for example, this applies for many different neural networks. For example, we have this one, this two-tower model, which is very used in retrieval models, which are the ones that are very interesting for us as a possibility for recommender systems. So we usually have it's called the two-tower because in one side we have the user, we generate the user embeddings, we take user features, we generate the user embeddings, then we use movie features and we generate the movie embeddings, then we perform a dot product between these two embeddings where we want, so we want to maximize this dot product in order to make the user embeddings converge to the space of the movie embeddings. So user embeddings should be as close as possible to the relevant items. So here, after the dot product, we will have, we will get like the ratings from each of our users to all of our movie embeddings. So this is something very particular from recommender systems that it's different from other machine learning problems, because here we have to give a rating for all of our space of items. So this is very expensive, but doing it this way is better than other approaches, because here with the dot product, here we are passing like each interaction in a event-based model. So we are not passing like the full matrix of interactions, which will be like very expensive. So here we are solving a little bit the problem of sparsity, because we are giving each interaction as an event to generate like these scores. So what do we need for the retrieval model? So we need user embeddings, we need item embeddings, and we need to then perform this dot product that will be a kind of a cosine similarity. So this is like beneath, it's kind of a matrix factorization. So for the ones who don't know a lot about embeddings, this is a kind of an introduction. On our case of text, embeddings are vector representation of words, and they usually capture semantic relationships and also contextual information. So it doesn't only work for text. We could have objects as images, audio, which then passes through a neural network or a transformer, and then we get these vectors that could be used then later to perform a task. So for example, object recognition for images, for text we could have translation, question to answer, for audio, anomaly detection. So we could perform different tasks with these embeddings. So how will it look like? So at the end, the idea is that these embeddings represent all these semantic relationships. So similar users should be like placed very similar in a similar space, like very close, and also similar movies should be placed very close on our vector space. So let's review a little bit how this retrieval model work when we have embeddings. So usually in retrieval models, we have a query, we have a full database like with all the possible recommendations or items that we want to in order to answer the query. But on this case, queries and matches, which are the ones that are the more close to the query, are embeddings. So our query will be an embedding, and our matches will be all the embeddings that are more close to our query embedding. So for example, if our query embedding is, I don't know, for example, Harry Potter, then the embeddings of movies of the sequel of Harry Potter and Narnia should be like on the matches, for example. So this is like the a pipeline for embedding search. So as I showed you before, we have first the preprocessing, we have the tests, we take them to a transformer, for example, then we generate the embeddings. Here we could also do some feature engineering in order to reduce the space of these embeddings. Then we have the encoding, so we generate the indexes of these embeddings, and we store them on a vectorial database, and then we perform the search or the querying through these embeddings. So how are we going to perform this search since we have embeddings for all of our items, since these embeddings could be also very big? So yeah, the only way to perform like an exact search, a very precise search, will be the brute force. Of course, an exhaustive search. However, this is too computationally expensive. Not only because we have like a lot of items or, but also because these embeddings have a really high, a really big dimensionality. So, for example, the ones that are familiarized with GPT models, the different engines from GPT can produce, for example, the ADA engine, it produces embeddings of a size of more than 1,000 features. So these embeddings could be really huge. So imagine to compare each embedding to all the embeddings, the query embedding to all the embeddings on a database. It will be almost impossible. So that's why the proposal of approximate nearest neighbors wants to sacrifice a little bit, like the precision and recall of the exhaustive search or brute force approach, in order to get a better time. So it's a trade-off always between precision and time. And anyway, these recommendations are like good enough. We usually have like 8 out of 10 good recommendations from movies, or 30 out of 50 images retrieved from a criteria. Then there are many, like libraries, algorithms that have implemented these efficient approximate nearest neighbors for high dimensionality spaces. So, for example, we have Annoy from Spotify, Fize from Facebook, hierarchical navigable small words, Scan from Google, and non-metric space libraries. So I think you will hear a lot about this during this PyCon, because I have seen that many of you are really interested of embeddings and these vectorial databases. So, for example, how does Annoy works? It takes the space of dots. It's like the logic. First, we have like the space of all the items or dots. Then we have like an hyperplane. It produces an hyperplane that splits the data set between two. So as you could see on the little tree there, so it starts like at the beginning, we only have like these two spaces, the green one and the blue one. Then these hyperplanes turn into like the main decision for a binary tree. So then it reproduces like this logic. So each of these spaces is going to be again splitted by an hyperplane. That will generate another binary tree. So at the end, we will continue like this process in order to build this big tree that we have here. And then when we look for a query, we will be able to find very easily which is the branch where we have the query. We could traverse the tree only for that branch. And at the end, we will get like a set of around 6 embeddings. So we have reduced very good this space. So then we will only have to compute the distances between all these embeddings and then rank them. Annoy even goes beyond this, because if we have trees, then we could also build forests. So from these trees, it builds also forests, and at the end, we have like an image like this. So at the end, it all converges to like a region of all these polygons where we could find the solution. So I put the link here for a better explanation for how a noise works. Then we also have the hierarchical navigable small word. So yeah, here the logic is like we have like an entry point where we start like our search. Then we go using a proximity measure, we go to the next neighbor that is closer. Then we go down to another proximity level. So on every iteration, we are like building like new planes, or new levels of proximity. And at the end, when we get to the kind of the last layer, we find like the nearest neighbor to our query vector. So this also uses a combination of randomized, random heuristic strategies. It uses a lot of tricks to perform this search very fast. So this algorithm has been implemented by different libraries, and we have like very proficient solutions like Kudrant, that is the one that we will talk a little bit later, which is a vector database and a vector similarity search engine that implements this algorithm, and also Python. Python implements the same algorithm. So the workshop that you will have on Sunday, it's about also vectorial spaces and the use of Python if you are interested in it. So remember that we are that we are interns at this startup of movies.com. So we are thinking about what will be our proposal. So we will use collaborative filtering, embeddings, and indexing. So first of all, since we are interns, maybe we still need like 2 months in order to get access to all the databases. So that's why we should look for maybe a public database in order to start with our solution. So that's why we selected the Movie Lens 20 million data set. So here we have movies data and also users data. We have more than 10,000 unique movies and more than 100,000 unique users. So we have from the movies data related to tags that describe movies, and we have a relevance for each of these tags. For ratings, we have like the interactions between users and movies. So we have like the rating that the users give to a movie. And that's our data. Then we are going to do some pre-processing to our data. So we will remove some of our movies which don't have a lot of interactions data. So we remove them, and then we create a new field that will be the description from summing up like the genres data with the tag data. We won't include the title because, as you may know, sometimes the titles don't describe very much like the content of a movie. So it was adding us like a bias on the search, so we are not taking into account the title. So now we could go, now that we have preprocessed our data, we can start generating the movie embeddings. So for the movie embeddings, As I mentioned before, for these embeddings, we usually use like neural networks, transformers. So we selected this structure algorithm. I put on the references the paper for this algorithm that it's very interesting. It is able to take a text data, and then it can generate these text embeddings based on an instruction. So in our case, our instruction is to represent movie metadata for retrieval. But it's really interesting because when you could have like the same text, but you could have different instructions. So you could have the instruction of a classification, and then your embeddings will be like specifically for that task, or for a question and answer or query and answer. So also the embeddings will be different. Now that we have our embeddings thanks to the instructor algorithm, we'll be able to get item-to-item recommendations. So finally, our first task. So for this one, we use Quadrant, as I mentioned you, the solution that implements hierarchical navigable search walls. So here, for example, we are able to perform a semantic search. When we look for the word Pixar, it's able to generate like the embedding of Pixar, and then look on the index of movies and find the most similar movies. So for example, to Pixar, we get the movies Up and Wall-E, and also Finding Nemo. And then we could also, from Up, we could find like similar movies to Up, which will be Finding Nemo, of course, Ratatouille, Toy Story. So obviously, we are really getting like recommendations that are very close to the categories or genres that we have. Then we have, built our movies embedding. So now we are going to focus on the users model. So as I mentioned you before, we decided to use the collaborative filtering model, and this two-tower model, you have seen it before in the presentation. But why is the movie embedding all in gray color? And it's because we decided to use the already created movie embeddings, and we will freeze like this part of the neural network, and we will only train our model with the user data. So we will try to force these user embeddings to converge to the space of the movie embeddings. So then we will calculate the dot product, which is like the cosine similarity, and we will maximize like these distances between users embeddings and the most relevant movie embeddings. Okay, so this is like the pseudocode for our model. So we firstly generate the movies embedding, the layer for the movies. So here we get like this pre-computed embedding, so this layer won't be trainable. Then we have the user embedding layer. This one we are going to train this one. Then for the training, we will have the dot product between movies and users, and then we will take this dot product and we will pass it through a sigmoid in order to get values between 0 and 1. So we could treat this problem as a classification problem. So that's why our last function is a binary cross entropy, and the optimizer that we use is Adam. So our training results were pretty good for 10 epochs of training. We got a mean average validation of 0.16 and also a root mean squares of 0.2, which was pretty good. And then how relevant are our results? So we have a mean average precision at 10 of 2%. So what does this mean? So it means that out of 10 recommendations that we do, usually 2% of them are relevant. But what do we call relevant? For us, like relevant is when we are able to recommend content that the user has already scored positively. But this is not for us like the main objective, because it's not so interesting to get the recommendations of the same things that you have already seen. But this is only to see that if we're able to recommend what we have already seen, but we will see that we're able to recommend items that are very similar on our genres and also on the tags of our movies. So now that we have the user embeddings, we will be able to perform user to item recommendations. So here we have the user optimistic bends. So here we are able to take, with Quadrant again, we are able to take the user embeddings and we can go to the index of movies and search for the movie embeddings that are more closer to our query embedding, which is the embedding of the user optimistic bends. So these are like the movies that Optimistic Bends has already targeted, like very good. Goodfellas, which is a crime drama. And then, for example, we recommended also some crime drama movies like The Fight Club and also American History. So yeah, we get like a little bit of similarity on the recommendations. This is another example. So here's also, here we also evaluate like precision and recall only for one user. So here, it means the number of recommendations. So here we are evaluating like how recall and precision change as long as we are incrementing our recommendations. So as we can see, this is very common, like recall, it's like kind of the same value, or it could increase. And then precision oscillates, of course, because precision is related to the amount of recommendations that we are doing. So now that we have our user embeddings, our movie embeddings, we will be able to perform finally the task that we were asked at the beginning, to recommend users to other users. And we will have, and we will have like we found like an extra interesting use case, and is that we could provide item recommendations to pairs of users. So I think for many of us, it has happened that we want to watch a movie. I know it happens to me with my father, that we have super different tastes, and it's super difficult to find a movie that both of us will enjoy. So we will see that we will be able to, given a user ID, we will be able to recommend not only other user IDs that enjoy like the same type of content, but we will be also able to recommend items or movies that both of us will enjoy. So I think, this is like really interesting, and it wasn't like difficult to do because we only needed to take the user embedding from both. For example, this user back vigilant, and Epic Nash is the other user. So we could take these two embeddings, then we make an average of these embeddings, and then we go to the index of the movies and search for the closest embeddings, the closest movie embeddings to this average user embedding. So that's how we are able to also recommend content that both people will really enjoy. So, for example, Vigilant Diffie is really loved. I know we can see a lot of children movies like Toy Story, Aladdin, Beauty and the Beast, and then all the users recommended also enjoyed this type of movies like Toy Story, Aladdin as well. And then we have recommendations of other movies that are kind of similar. Backdraft, well, I haven't seen that one, but Speed, yeah. So you can go. So some conclusions that we have. So we were able to create movie embeddings using the structure model, which was good enough to represent our movies features. We were able to perform also semantic search on our movies indexes. We also create collaborative filtering model, leaving the movie embeddings freezed, and we got a root mean square error of 0.21, and also we got a mean average precision at 10 of 2%. We generate movies and users indexes using hierarchical navigable small words algorithm using quadrant to get recommendations of user items, item to item, and user to user. And we were able to also do joint recommendations from couple of or pairs of users. Two pairs of users to see like content that both of them will enjoy. We have like references, and that's it. If you want to work at Factor, you can reach me out. We always are looking for all these positions. And thanks.